Hey everyone, Carlos here from Dev at Fiveonefour. In this video, we're going to look at brainwaves and go from capturing raw streaming EEG brainwave packets to a queryable analytics table with APIs, locally, fast, and without glue code. To speed up development, I use Moose, a modern framework designed for building analytics applications. Using Moose, I was able to stitch together a UDP listener, a stream processor, a database, and an API, using one project and one toolchain. If this brainwave stuff isn't totally new to you, then bear with me, as I provide context for the rest of you who might be learning about this for the first time. Okay, let's get started. Your entire body generates electrical activities. Your brain, heart, muscles, even your cells spark with electrical activity every second. It's not science fiction, it's biology. And in this regard, your brain and heart speak the loudest. That said, they speak in barely detectable whispers. This electrical activity was first measured in animals by Richard Canton, an English physician and physiologist. In 1875, Canton recorded detecting electrical current from the exposed cortical surface of rabbits and monkeys. Those electrical currents are what we now know of today as EEG signals. However, it was German psychiatrist Hans Berger who first recorded the human EEG. Berger began recording from human subjects with skull defects in 1924 and introduced the term electroencephalogram in 1929 when he began publishing his work. Now, as you can imagine, the instruments used to measure electrical activity have dramatically improved in the past 150 years since Canton's early work. In fact, the device I'm using is an ultra-lightweight device that works with your phone to record and visualize brainwave data. It's likely that such a device was inconceivable by Canton and Berger. So what's the big deal? Why record electrical activity from the brain? What are the benefits? Monitoring brainwave activity has been described as eavesdropping on the communication signals generated by the brain's mass of neurons. This helps scientists better understand how the brain works and provides detailed insights through the analysis of various brainwave frequencies like alpha, beta, delta, theta, and gamma. This is all pretty fascinating stuff. And if you're interested in learning more, your favorite LLM can tell you more than you're likely to want or need to know. For now, let's move on. I'm going to demo two core apps and a script as suggested in these three panels. On the left will be an app called DAS, the Data Acquisition Server. DAS is a Node.js and TypeScript application that receives UDP data packets that contain brainwave, heart rate, and movement data. To its right will be BrainMoose, a TypeScript app that is built using Fiveonefour's open source Moose product. BrainMoose will be hosted by the high-performance Moose framework, which is written in Rust. As a side note, Moose currently supports building applications in your choice of TypeScript or Python. Moving right along, BrainMoose is designed to ingest, process, and analyze brainwave session data, providing endpoints for reusable logic and downstream applications and dashboards. It leverages Moose's strong typing and data pipeline features to make it easy to build, extend, and scale data and analytics-based applications. Lastly, on the lower right panel, I'll run a simulator script that reads data from a CSV file and sends it to DAS as UDP packets. DAS in turn receives the data packets and builds HTTP messages to post to BrainMoose, ingestion API endpoint, and pipeline. Now, because the vast majority of folks won't have a Moose headband, I'll demo how to download a brainwave dataset and use the included simulator to send data to DAS. Let's run the download script, which will download 4 CSV brainwave data session files, one for coding, one for meditation, another for exercises such as push-ups, sit-ups, and leg lifts, and the last one for a Chinese practice called Qigong. Okay, next let's run the DAS app, and here we'll start a session called coding. DAS loads with a terminal UI showing panels for heart rate, brainwave activity, raw data, and system log to show some behind-the-scenes activities. Now let's switch over to the right panel, where we'll start our BrainMoose app. Moose launches a set of Docker containers for use by our app. We get a ClickHouse database, a Red Panda container, and a Redis container, all running in a Docker Compose stack. Cool, our Brainwave app is up and running and listening to port 4000 and ready to receive data at its ingest API endpoint. DAS will take the data it receives via UDP and send it in an HTTP post to Brainwave. Brainwave will in turn ingest the data and queue it into a Kafka data stream, where it will then be written to our local ClickHouse database. Because in practice, data from an actual hardware device would be arriving at hundreds of UDP packets per second, this architecture is both highly efficient and scalable. Pretty cool, huh? Let's go ahead and start our simulation script and send it, the brain data for coding. This will send streaming data via UDP. Oh, and using this simulator support means we can iterate without an actual headset. Notice the heart rate, readout, alpha, beta, theta, and gamma waves. Below that panel, we see raw 3D movement data from the onboard accelerometer and gyroscope, along with raw brainwave data. And below that, we see the behind-the-scenes system log of activities. The last bit of this demo I want to share is a look at the actual ingested data in our local ClickHouse database. Here I'll use DataGrip, but you can use any SQL client that has a ClickHouse connector. In closing, consider that in minutes, we went from ingesting sensor data to a queryable database, ready for dashboards, ML, and AI. That's made possible using Moose streaming and processing. And now we have the ability to analyze data in real time, end-to-end locally. That's it for this demo. In the next demo, we'll look at using AI-powered analysis, using the Aurora MCP server running under the Cursor IDE.